Thank you, Al. Good afternoon. Materials Innovation Platform to the Resident Scholar Visitor Program, RSVP Symposium for 2025. I'm Dr. Ronald Redwing. I'm an Education Outreach Coordinator for the 2DCC, and I assist Kelsey Maxim, who is the RSVP Program Director. So what is the RSVP program? It is a program that the MIP uses to collect individuals to come here to train and to do research. And unlike programs like our undergrad research program, the proposals are generated from outside, the ideas, the training by the needs of the potential fellow. So what does an application look like? And the speakers today went through the process of filling out our online application form, giving us a CV, obtaining a letter of support from their advisor or supervisor, and then writing a short training/research proposal of what they would like to do at the 2DCC and how our facility helps them along their career. This proposal, next deadline is January 31st, 2026, then goes to a committee which is composed of Kelsey and myself, leadership from 2DCC, and probably most importantly, potential hosts from all the different areas of research in the 2DCC. And it's evaluated on merit and broader impacts. So today we're going to hear from the results of the last January's selection committee and the selected folks who are now going to talk about their time and extended time after results from their successful application.
Awesome. So Shyam Karullithodi from Florida State and the National High Magnetic Field Laboratory will be going first. So Shyam, the floor is yours.
Thank you, Kelsey, and thank you, Rashidul. So let me. Can you see the slides? Okay. Yep. Good afternoon, all. Myself, Shyam Karullithodi. I'm a fourth-year graduate student at the National High Magnetic Field Laboratory at Florida State University. And today I'm very happy to talk about my summer research that I've done at 2DCC, heterostructures of layered ferromagnets for imaging and simultaneous transport measurements as a part of a Resident Scholar Visitor Program 2025. So first of all, I would like to thank 2DCC Material Innovation Platform at Penn State University and the Department of Physics for giving me an opportunity to conduct my summer research. And I would like to thank Professor Junsu, who was my host at Penn State, and Patrick and Carlton for their all trainings. Of course, all other Zoo Lab members for a wonderful working atmosphere. I would like to extend my gratitude to Kelsey, Stacy, and Melissa for all the administrative help. And I would like to thank my TI at Florida State, Dr. Luis Pelicas, for recommending me for this program. Also to Dr. Ueli at Argonne National Laboratory for all scientific advices. So this is a brief introduction to my program. So I spent my summer from May 12 to June 28, roughly around 7 weeks at 2DCC. I was mainly using the inert atmosphere cluster tool for the fabrication characterization of air-sensitive 2D materials and devices, basically the 2DCC glove box. So when I'm looking back, my major learning outcomes from this program was getting a basic understanding of the experimental techniques for device fabrication, starting from cutting and cleaning of silicon dioxide wafers, mechanical exfoliation of graphene and iron 3 gallium telluride 2 or FGAT, that is my material of interest, and doing atomic force microscopy of the exfoliated samples within the glove box, and stacking of different 2D material heterostructures, also micropositioning and transfer the stacks to the desired substrate. In my case, it's an LTEM grid. So before diving into the device fabrication process, let me give a brief introduction to the motivation for this project. So our group is mainly interested in understanding the topological magnetic materials and material which can host topological spin textures for various device applications. So spin textures are spatially varying magnetization configurations which are protected by their topology, a wall-like spin textures that have a non-trivial topological charge. For example, skyrmions, mesons, etc. So even skyrmions can have different types, like Neal-type skyrmions, where the spins are aligned from radially outward, where Bloch-type, they are aligned tangentially in the plane. So in this project, we propose to study within a combination of transport and imaging techniques, such as Lorentz transmission spectrum microscopy, can we get the lifetime of the skyrmions or their sizes and width as the thickness of the channel or crystal is reduced? Also, the critical current that required to move the skyrmions within the channel. So that was the main motivation for this project. As you can see in this image, if we can manipulate the spin textures within the crystal, we can use this for various applications. So let me explain the device structure that we aim for. So what we got is like a LTEM grid, as you can see in the figure. That's a silicon grid with a silicon nitride membrane. It has 9 windows, which are the TEM windows. So if we transfer our material on top of these windows, we can do the TEM imaging. So that is, windows are made up of silicon nitride. The thickness of that membrane can vary from 15 nanometer to 50 nanometer. So we are interested to make a stack of graphene and iron 3 gallium telluride 2. So iron 3 gallium telluride 2 is very air sensitive. So we have to cap this material with graphene for protecting from like air. So in this particular project, we are interested to make electrical contact to this TEM grid and transfer our graphene FGT stack on top of this contacts. So that was the main motivation. And by applying current, can we manipulate and can we move this in texture or skyrmions? So that was the question that we were asking. So as you can see, I plus and I minus are the current contacts and V1, V2, V3, V4 are the voltage drops. So I started with learning the mechanical exfoliation of the samples. So for that, I exfoliated graphene on top of silicon dioxide wafers. So the first step was to cut and clean the wafers. That for I used ozone treatment, acetone, and IPA cleaning. So this is a very basic cleaning procedure. And I exfoliated graphene and also iron 3 gallium telluride 2. So you can see the exfoliated iron 3 gallium telluride 2. And what I felt interesting was that in 2DCC, in the glove box, we have an AFM within the glove box. At Florida State, we don't have that facility. So when I exfoliate the flake, I can directly take the AFM and to see the thickness and the surface topography without taking it outside. So you can see the AFM image. The thickness was around 90 nanometers for this sample. So also I have done this exfoliation for graphene. And for my project, I need like a few layer thick graphene. I don't need to go for a mono or bilayer limit. A few layer thick graphene is fine. So also I have done exfoliation of graphene and do the successive AFM imaging. So after exfoliation of the sample, the next step is to make or to pick up the sample from the substrate. So for that, we make a PC polymer stamp, which can pick up the exfoliated flakes from the silicon wafer. So first, I pick up graphene from silicon oxide. For that, we in the glove box, we had the transferring setup where we increase the temperature up to 120 degrees Celsius and slowly pick up the graphene using a stamp. Then after the stamp, graphene stamp, we will use the same stamp to pick up the FGAT from PDMS. So this was the transferring process, pickup process I was following. And the main challenge I had during the project was how to give electrical contact to the grid. So as I shown earlier, I had to give electrical contact to this a suspended membrane. This was not a flat surface. It was a suspended membrane. So for that, electron beam lithography was not very trivial. And we were thinking about different other alternatives, such as making a mask uh, to make electrical contacts so that I can avoid the electron beam lithography process. But due to the time restrictions, I couldn't do much making electrical contacts. So what we planned was I will make the stacks and I will transfer the stack to the grid, and later we can do a top contact. So I drop down all my stack to the LTM grid by applying a temperature of 180 degrees Celsius. So giving 180 degrees Celsius, this PC polymer will completely melt and my sample or my stack will be transferred to the grid. And later we will wash off our polymer residues using chloroform. So these are the different stacks that I made. We can see picture A to picture F, the material that I successively transferred to the LTEM grid with a graphene top layer. So the main challenge was after transferring, I need to wash off the excess polymer. You can see there is a gray color polymer residue. So I have to wash off this using chloroform. Unfortunately, most of the time when I was trying to wash off this polymer, my sample will be dislocated from the grid position. The silicon nitride membrane is not very adhesive to the flake. So when I was washing with chloroform, this flake will just move from its position. So after such, I think I made 6 or 7 stacks, but 1 or 2 was only survived till the end. So in conclusion, I learned basic experimental techniques for nano device fabrication, which includes mechanical exfoliation, stacking of heterostructures, and transferring to the substrates. I had a lot of troubles with dislocation of samples from the grid position when I was trying to wash off the excess polymer residues. So after returning from 2DCC, I was basically working on making electrical contacts to the grids and then transfer my samples. So a couple of weeks before, I successfully make some contacts, but still I am working on that now to improve the quality. Thank you.
Thank you, Shyam. Does anyone online or in the room have a question for Shyam? Okay, so our next speaker will be Olivia Fairlamb from Kenyon College. And Olivia, you are good to go ahead and begin whenever you're ready. Thank you.
All right, so slides should be up, audio should be going. We all good?
Yep.
All right. Hi, everyone. My name is Olivia Fairlamb. I am a senior physics major at Kenyon College, which is a small liberal arts school out in rural Ohio. So it was really exciting for me to come to Penn State and get to use the 2DCC facilities at a big school and see what like a big lab is like. So this summer I worked in Dr. Joan Redwing's lab under the supervision of Dr. Andrew Graves. And we were working on using in situ spectroscopic ellipsometry, or SE, to monitor the growth of thin tungsten diselenide films using MOCVD. So the motivation here is we want to improve the fabrication of these films. The Redwing Lab specializes in MOCVD, where we are growing thin materials for use in electronics, especially in transistors, and transition metal dichalcogenides like tungsten diselenide are particularly optimal for their good semiconducting properties at thin layers. In order to have more transistors on a chip, we want to have them be smaller and thinner, and the TMDs are particularly good at maintaining those properties at very thin levels. So this growth, the metal organic chemical vapor deposition, happens in the MOCVD reactor, where gas is deposited at a very high temperature. Our growth temperature was 1,000 degrees Celsius onto a sapphire wafer, which serves as our substrate. So we were growing tungsten diselenide this summer. And the beauty of this project is we have the spectroscopic ellipsometer attached to the reactor chamber. So we can take in situ SE data. meaning the data happens during growth, so we can get one, live feedback, and two, data that can be taken without the sample being exposed to the atmosphere. So that's the way that we were using it to monitor, is having that active data during growth. The SE itself is a measure of the change in polarization of light that strikes the sample. The light strikes the sample and is reflected back into a detector, and it outputs this psi and delta spectrum. So these spectra can be modeled to obtain the optical constants N and K, being the index of refraction and the extinction coefficient. I use epsilon1 and epsilon2, which are not exactly equivalent one-to-one N and K, but they do represent the similar quantities. So to break it down further, we have this spectra of psi and delta. I then make a model for the optical constants epsilon1 and epsilon2. Those can then reconstruct a psi and delta model that predicts what it should be for these certain scenarios. So what we can fit for is something like the coverage percentage. So that EMA percent is what percent of the material on the substrate is what we are modeling as the monolayer. So we can get an idea for, at this moment in time, how much of the substrate is covered by the monolayer tungsten diselenide. So if we can apply that in situ, we can get a real-time monitor. So we confirmed this by using this time series data where tungsten diselenide was grown for various amounts of time. In this table, we go from 0 to 13 minutes, and that was enough data that for each time, you get a different coverage, which we then confirm with AFM what that percentage might be. So then we can understand how the sample, the monolayer, grows and covers the substrate as a function of time. So we can calibrate and make sure that we're getting kind of reliable data. So then we've been looking at these static single time slice psi and delta spectra. We can also take data that goes over time. So this is some dynamic data from a growth where we have a different spectra taken at each moment, and we can put those together. So instead of just having the one time slice and fitting at that time slice for the coverage percentage, we can then get a function of time and see how it's developing based on how the spectra change. Then we can compare that to the AFM confirmed data. So let's look at that graph. This was the first iteration of my model that I applied dynamically, and we can see in general we have kind of a linear shape, which we would expect for the growth. Obviously, there's some noise in there, but in general, we see coverage is increasing as time goes on. That makes sense. It's not too far off from the data. We do see that it doesn't agree as much at the low coverage end. We would expect, because we start this SE after nucleation has begun and when we're in that lateral growth step of MOCVD, that we would expect that it's starting with maybe 14% coverage, and the model only starts showing up at 40%. So there's some disagreement there. So we have to ask what could be going on. So I did an investigation. I went back to how I was structuring my model. The way it was working in the software, which is Complete Ease from the J.A. Woolham Company, we have a model for the sapphire substrate. And on top of that, we have this EMA, which is where I'm measuring that coverage. So for example, if there were 40% monolayer coverage, it would be only 40% of that model is where I'm plugging in what I have set for the monolayer. The other 60%, I'm saying there's nothing on the substrate, so that's void, which is fixed in the software. So that top layer, we feel pretty confident in. So what's going on with the sapphire? Could that be something that's going on? Sapphire is an anisotropic material. That's how we treat our wafers. And so I was using this uniaxial type model in the software in that gray box where you can put tabulated files for the ordinary and extraordinary sapphire from the software library. And that is assuming a perfectly transparent sapphire, and the data comes from sapphire at room temperature, which again, we're at 1,000 degrees Celsius and it's a pretty intense environment in there. There's some other things going on. So what does the sapphire actually look like? We have some data of sapphire SE at growth temperature, where we see that the model I had been using are those black and white dotted lines. And I've highlighted the one that should be modeling delta is that one in that kind of orange color, where we would expect for it to be transparent, that it should be completely zero. Delta is representative of absorption. So what we're seeing with that green delta data is that there is a non-zero absorption at that high end. So there's something that is being absorbed and being not being counted by the software as the sample when it is perhaps from the substrate. So what I did was I made a custom model where I assumed that something non-ideal was going on with the sapphire. It wasn't entirely transparent. Applying that model resulted in this graph where we see this red fit for the custom sapphire, where obviously there's this vertical thing that's happening that's still a bit questionable. So at the low energy end or low time end, there's still something to look for and fix, but we got much better agreement with the AFM confirmed data. There were some issues where we saw a higher mean squared error between the predicted psi and delta and the data psi and delta. So that's the current issue that I'm trying to resolve, is understanding how the sapphire is behaving and why we might get a more accurate coverage, but a less accurate psi and delta fit. So this is my priority, because if we can figure this out, we can look at other perhaps potential applications where we might be able to, if I can have a model for different dopants, then if we were to p-dope or n-dope the films, I could get a live coverage concentration of what the dopants are. And then another thing we're looking at is for this phase variance, because TFDs have the 2T and 1H phase transitions that we see sometimes during growth. And it would be very interesting if we could track that as it happens and know when, for example, the 1T phase might appear and then disappear by the end of growth. So it would be more informative. So to summarize, the SE can give us an insight into what's going on in growth as it happens. We can get that dynamic in situ model from the static, and that the substrate has a non-trivial effect. And so it's very important to be precise and physical. And if we can work all of that out, we can get to some exciting applications for the future. So I would like to thank all of these people who assisted me in this project and getting me here. I'd like to thank the funding, and I'd like to thank everyone for listening. And I'd be happy to take any questions.
Thank you, Olivia. Does anyone online or in the room have a question?
I have a question. Do you get any growth on the window?
The growth on Windows, is that the question? I believe that that was something that we had talked about, and that there is a certain amount of deposition that can happen on the windows, but there are precautions that are taken in order to minimize that effect. And I believe, I now can't recall from when I was there in maintenance week if that was something that was taken into account and cleaned when we opened up the chamber. But yes, there were times where we were considering, like, could there be something that was depositing, especially we were having some issues with depolarization of our light. That was something that we thought about, but I think that we determined the effects, if there was any deposition, were negligible at the time. But yes, thank you.
Thank you.
Yeah, I guess I just had a really quick question. Do you have any idea of what is happening with the sapphire, like why it's absorbing?
Yeah, so we had some ideas of, like, it could be that there might be some sort of interfacial layer of, like, there might be something happening, some deposition on the sapphire. It could also be that it doesn't show up just on, like, plain sapphire at high temperature, but maybe in the chamber where we have those gases, there could be some, like, initial etching that's going on, and that's changing the texture at the surface and causing some sort of absorption to be happening. So yeah, that's like one of our biggest questions. So, like, I want to know the answer to that question too. But yeah, those are kind of our going theories at the moment.
Thank you.
There is a question. Do you know if you used a double-sided polished sapphire or it was single-sided sapphire?
It should have been, polished just on the surface. It should have been rough on the back so that it's not, you know, yeah.
Thank you.
Thank you, Olivia. And our next talk will be from Huayuan Han from the Rochester Institute of Technology. And Han, you are good to go ahead and get started as soon as you're ready.
Thank you, Cassie. Let me share my screen real quick. Can everyone see my screen?
Yep, we can see it.
Okay, is it in the presenter view, right? Or
it's not in presenter. Oh, now you're good. Yep.
Okay, cool. Thank you. So Hi everyone, I'm Huayuan, and I'm a master's student from RIT physics program. And then for this work, I'm working with Dr. Robinson's group on to grow the high quality 2D 3-5 material via CHETS method. So some quick background. So why do we care about 3-5s? So 3-5 material generally have wide, large bandgap, which help for light absorption range. However, indium arsenide as a 3-5 material is actually sitting in the opposite corner of 3-5 material, where it has a super narrow bandgap. So then why do we care about using indium arsenide? So the advantage of using indium arsenide is that it has tunable and direct bandgap. So even though it has a really small bandgap, but it is highly sensitive to infrared range because it has such narrow bandgap, which give a great potential in using in detector and lasers. And also for thin film indium arsenide, it has a thickness dependent bandgap. So this range that you can actually play with thickness, and papers have been demonstrated in both theory and experiment data. And also the indium arsenide has the large carrier mobility, benefit to use it in high efficiency transistor or nanoelectronic devices. It's almost 20 times higher than silicon. And however, the challenge for growing high quality 2D indium arsenide is that, first of all, it has this material has a strong covalent bonding, so it's hard to, it's not intrinsically a layer by layer material. So in order to grow it, to confine it to completely lateral growth is a challenge. Second is it has it usually has a non-uniform growth property because indium arsenide has a lattice about like 6.6 angstrom, which is much larger than the common substrate, such as silicon and sapphire. Therefore, as you grow the material, such lattice mismatch will induce higher energy as the layer number increase. So from this literature, it has demonstrated that as it's an AFM image, and as you can see, as the layer number increase, you gradually see a higher density of this 3D indium arsenide island shown in the bright spot. And here's a SDM image of show the cross section. So that's the second challenge. And third one is, even though people have successfully grown thin film indium arsenide, however, such material is similar to other 2D metal or semiconductor, it's really easy to oxidize. So you can see, even though they achieve a layer of 0.35 nanometer, which is a monolayer, actually, but it does have the significant indium oxide and arsenic oxide peak from the XPS data. That brings us the motivation to use confinement hetero expectancy, as known as CHET method. The general process for CHET is that first we're gonna have silicon carbide substrate, and then we're gonna do a silicon sublimation, remove the silicon atom, and grow the multilayer graphene on top of the silicon carbide. And then we will do a plasma treatment to generate defects on such substrate, which will open the pathway for atom to integrate between the multilayer graphene and silicon carbide interface. As you can see the schematic here, but I would like to draw your attention to here. So as we grow multilayer graphene on top of silicon carbide, the bottom layer, even though it has the graphene structure, but it doesn't really have the graphene property because it is still bonded to the silicon carbide substrate. That I will talk about in later, detail in later. But as you integrate the atom, it will actually decouple the bonding between the bottom layer, we call it buffer layer graphene, and the silicon carbide substrate. And then upon the atom integration, after we grow, and the graphene will actually self-heal and preserve the integrated atom underneath the multilayer graphene from oxidation. And at the bottom is XPS and Raman data to show how we how does the graphene progress as we during the growth process. So we can start from XPS. So interestingly, you see all the peak stick together, where the buffer graphene, the top layer graphene, and also the silicon carbide substrate. However, as you integrate, you'll see this carbon peak splitting that confirm the decoupling of the graphene and the silicon carbide that shows atom integration. And also on the ramen, you'll see at the bottom is the ascron graphene. It doesn't really have the full fingerprint of graphene as we know, the D, G, and 2D peaks. And as you treat it with the O2 plasma, you see a significant increase in the D peak, which implies increasing in the defect density, which is the pathway for integration. And as you integrate, this D peak decrease and the G peak, while the G peak increase means that the defect will actually self-healing while the atom integrate, decoupling the bonding between the buffer layer and silicon carbide substrate, and have this improving the graphene quality. Basically, that's what the increase in GP means. Yeah. However, for to use and thoroughly use chat for indium arsenide growth, it still has a few challenges. First of all, is the interface arsenic atom integration. So arsenic atom is less likely to it's hard to stick to the silicon carbide substrate. Therefore, we need something for it to bind to. And that's why we are breaking the growth process into two steps. We're going to grow and integrate indium first, and then arsenic. However, that brings us another issue is that indium tend to deintegrate usually about 300 degrees Celsius. While this happens, that makes this two-step growth even harder, because as we do plasma treatment, integrate indium, and then we do plasma treatment again, and then do arsenic integration. During this process, we might lose some indium atom due to this integration effects. Therefore, we need to find a solution to this, and since and especially when no arsenide compound was grown with chat before. And to improve this, to get a better result, our new alternative chat method is that we decided to use 100% defective buffer graphene. So this will decrease so we only remaining the bottom layer buffer graphene for integration. So it gives us a higher chance for to induce the arsenic atom. And while we are also using two-step annealing process when we grow the arsenic atom. So the first step, where we are using TBAS as a arsenic precursor, because it has a low decomposed temperature. So when we process, after we have the integrate the indium sample, lower temperature will reduce the chance that it will deintegrate. That's the motivation for this step. And then and during this process, we're keeping a max flow of arsenic to ensure that the arsenic atom is bombarding the substrate instead of diffusing out, diffusing away from the substrate. And the second process is also occur at a higher temperature, and that's why we use a different precursor that decomposes at higher temperature. So in this process, after we bombard the arsenic onto the substrate, well, in order to fully convert the arsenic at near the integrated edge, we're gonna have this high temperature process to diffuse the arsenic atom and have a fully conversion into indium arsenic. And here are some here are some data to show that we have successfully integrated to the indium under the buffer graphene during my first visit. So for the left side, please pay attention to these two plots of Raman and XPS. So as we integrate, we do see sorry for the quality of this ramen data. That's my processing mistake. But anyway, so we do see the three 2D, G, and D peak of graphene that give us the decoupling from as we integrate indium atom, and also we see this carbon splitting from XPS data. And also on for the indium, we do have some issue here. So as we integrate and do ramen and to try to locate the indium signal, however, what we see is actually a big bump near the this 21 wavelength, because this contribute from the indium oxide. As I mentioned earlier, since we're using a defective buffer sample, that means this monolayer graphene might not fully protecting our integrated atom from oxidating, and therefore it might just covering all the indium pristine indium signal. However, we can still confirm we do have some indium that is integrated from the XPS. And then our hypothesis at this step, our hypothesis is that even though it has some kind of oxidation of the indium, but during the arsenic growth process, it might still be able to convert into indium arsenate, metallic indium arsenate during the high temperature growth process. Therefore, we took the sample back to RT and for the use it in the MOCVD chamber for the arsenate integration. The good news is we do see some evidence of the indium arsenate from our ramen data, which shown by these two peaks. However, the XPS does give some does weaken our evidence a little bit, because as you can see from both indium peak and arsenate peak, since the arsenic oxide and indium oxide, so the indium oxide peak and the indium arsenic peak are close together. So in here from the XPS, we do see a really strong oxide peak signal that might cover overlap with our indium arsenic peak. So that actually weaken our evidence, because if we see oxide, then we might not be able to show that the indium arsenate is fully underneath the graphene, which is the high quality 2D one signal. So that's what I've done from during my first visit. Therefore, in order to look for hard evidence, we need to confirm we did integrate high quality fully metallic indium first, and then we're gonna attempt another arsenic growth after the next visit. Yeah, so my plan for my next trip will be first we need to fine tune the recipe for which Dr. Cheng Yedong will I think is currently working on, is to obtain a higher quality buffer graphene sample. So it will reduce the chance for indium to oxidize first, and then we will have a better growth recipe for the purely metallic indium, so we can have a higher conversion efficiency when we bring the sample back to RT for arsenic integration. Yeah, and that concludes all my work during the first visit. Thank you so much.
Thank you, Han. Does anyone online or in the room have any questions? Okay. So our next speaker will be Kaiming Liu from the University of Illinois, Champaign, Urbana. And Kaiming, you are good to share your screen and get started as soon as you're ready. Thank you.
Okay, so can you see my screen?
Yep.
Okay. Okay, so I'll get started. Okay, so hello everyone, my name is Kaiming Liu. Today I will present our recent progress on the MB growth of chromium antimony on chromium ditelluride on iron telluride on STO100 as part of the 2DCC collaboration. Here's a quick outline for my talk. I will start with the motivation and calculate the joint density of state simulation and the sample growth. Then I will go through the read AFM XRD results. After that, I will share some data analysis and future directions, and finally, acknowledgements. So first, I want to quickly introduce the concept for altermagnet. So in ferromagnet, I will compare the concept with ferromagnet and antiferromagnet. So in ferromagnet, spins are parallel in real space, so it have net magnetic moment. In momentum space, energy band show unidirectional splitting. And in traditional antiferromagnet, spins are antiparallel, so the magnetic moment is cancelled in real space, which means it have no net magnetic moment. So in momentum space, energy band don't have spin splitting. In altermagnet, spins are antiparallel, so it don't have net magnetic moment too. However, the sublattice are connected by not inversion or translation symmetry, but rotation symmetry. So in momentum space, the energy band have alternating spin splitting. So after we know the basic concept, to have a better understanding for the band splitting, we need to compare the symmetry between antiferromagnet and altermagnet. For altermagnet, the spin-up electron and the spin-down electron shares the same orbital, so it doesn't break the time reversal symmetry, so the energy band does not have splitting. For altermagnet, since the sublattice have rotation symmetry, so the spin-up electron and the spin-down electron's orbital have an angle with each other, which will break the time reversal symmetry. And this will generate the alternating spin splitting. The altermagnet case is critical for our motivation, since it may produce novel proximity-induced effects when it interfaces with the superconductor. So in our lab, we focus on chromium antimony and manganese telluride since they have much larger spin splitting, which is easier for us to observe the phenomena in the experiment. So we have two motivations for this altermagnet system. The first motivation is to study the spin polarized QPI signatures in altermagnets with spin polarized STM. And the second motivation is to explore proximity-induced superconductivity and potential Majorana modes at interface between altermagnets and the superconductor. So let's take a look at chromium antimony structure. The chromium antimony has a layered structure. The two chromium sublattices are related by rotational symmetry, which breaks the time reversal symmetry without net magnetization. And this leads to altermagnetism and causes momentum-dependent band splitting. On the right, the APAS data shows clear band splitting along different directions, especially visible in the second derivative maps. So this is a model. After I go back to UIUC, I do some simulations. I use this model to simulate the quasi-particle interference for chromium antimony. So from APAS data in this paper, we know the real constant energy contour in chromium antimony are not perfect triangles. They have rounded curved edges. So here we used a simple trig function to mimic that shape, which is still threefold symmetric but smoother. As you can see, the resulting joint density of states and the spin polarized QPI looks more realistic, and the features are richer, and the overall pattern is closer to what APAS and STM might actually show. So beyond quasi-particle interference, chromium antimony also is interesting for interface studies with superconductors. As shown here, the TC for this heterostructure, chromium ditelluride and iron telluride saturate at 12 Kelvin, when chromium ditelluride is thicker than 4 layers and iron telluride exceeds 15 layers, which is a good substrate for grow chromium antimony. And here are the 3 growth recipes we used, which is I learned from Penn State. from Professor Sarma's group. So we first grow chromium ditelluride on ion telluride on STO100, and then chromium antimony on chromium ditelluride on STO111. And finally, we combine two recipes together. So for the first recipe, this is the read results for the first recipe, chromium ditelluride on ion telluride on STO. So ion telluride gives a nice streaks showing smooth growth. After adding 1 unit cell of chromium ditelluride, the read pattern stays sharp and develops a bottom fork, which indicates that chromium ditelluride has formed. And the growth temperature for chromium ditelluride is, the substrate temperature is 285, and ion telluride, the substrate temperature is 315 degrees Celsius. So the XRD 2-zeta scan of this sample, for ion telluride, it shows 001, 2, 3, 4 peaks as expected, and STO substrate peaks at 100 and 200. But chromium ditelluride is too thin to give a clear peak. And here's our AFM results of 1 unit cell chromium ditelluride on ion telluride. The island shapes are square, which matches the ion telluride structure, which means a chromium ditelluride is too thin to show up clearly. For comparison, we compare our sample with our AFM results with Professor Cuizu Chang's results. So they grow 15 layers of chromium ditelluride on 40 unit cell ion telluride. So in their sample, their ion telluride shows perfect square shape, and the chromium ditelluride shows perfect shows triangle shape, which is different from ours. Which means our sample might the chromium ditelluride is too thin to show up clearly. And this is the read results for the second recipe, 15 nanometer chromium antimony on 1 unit cell chromium ditelluride on STO101. You can see sharp streaks and clear 4x1 reconstruction after chromium antimony growth. And the growth temperature for chromium ditelluride was 296 and the chromium antimony at 287, with a chromium and antimony ratio of about 1 to 10. And here's XRD results for this sample. We clearly see chromium antimony 002 and 004 peaks, and STO101 substrate peak. So chromium antimony is only 1 unit cell, so it's still too thin to show up here. And AFM result of this sample is really good. It shows the chromium antimony terrace with a roughness about 1.3 nanometer and terrace size about 50 to 100 nanometers, which is flat and large enough for STM measurement. The third recipe is combine the first and the second together. And the read pattern for ion telluride is streaky, and the read pattern for chromium ditelluride is streaky and have some forks at the end. So after grow chromium antimony for 2.5 hours and 5 hours, the streaks remain but become dimmer, which indicates the three-dimensional island formation. Possibly a three-dimensional island formation in some regions. The read pattern suggests chromium ditelluride did not fully cover the ion telluride, which lead to the chromium antimony nucleating on some certain areas, which have chromium ditelluride, and it forms tall islands, which means we need to optimize the recipe continually. And the AFM results confirms that chromium antimony did not form a complete layer, and chromium ditelluride grew preferentially on islands, which yielding very tall features. And the surface roughness is very high in these regions, which is unsuitable for STM measurement. And the XRD results shows chromium antimony 101 peak, and 1 unit cell chromium ditelluride remains too thin to detect, and ion telluride shows the expected peaks. So chromium antimony peak confirms its growth, but combined with AFM topography, it is not ideal, and the phase is different. So I want to thank for everyone in Penn State helped me to develop the recipe, and thank also the funding for GDCC program. Thanks for the support, and thank you all for your attention.
Thank you, Kaiming. Does anyone online or in the room have any questions? Okay. Our next speaker will be Rashidul Alam from the University of Alabama. And Rashidul, you are good to go ahead and get started as soon as you're ready. Thanks.
All right. Thanks, Kelsey. Can you see my screen?
Yep.
All right. Hello, everyone. I'm MD Rashidul Alam. I'm a graduate student at the University of Alabama. And this summer, I have been doing RSVP training under Dr. Kolik and Dr. Wait a minute. Sorry. Yeah. So this summer, I've been doing my RSVP training under Dr. Kolik and Dr. Mayo of Dr. Van Duyn's group. And the topic of my project was to validate, evaluate a reactive potential. Now, this reactive potential was actually meant for the heterostructure synthesis of different TMD materials, especially molybdenum and tungsten derived chalcogenide materials. And a little bit of background. We all know that TMD materials, transitional metal dichalcogenide materials, they are mainly growth by CVD growth. And by CVD growth, we all know that we need a precursor gas and also in the presence of carrier gas, and we put them in the furnace, and the furnace, after heating, that creates a nice 2D materials on top of the substrate. Now, when you add multiple precursors at the same time, you will see a heterostructure being grown. And now this heterostructure is actually an important or interesting materials because these structures have multiple lattice parameters inside in it. So it creates a different strain in the material, and that creates interesting properties like the band gap differs in the same material, and also you will see different phase transformation inside the material. And also the second thing, interesting thing is like the growth parameters for these both precursors and both the species are different. So that means it is an interesting research to do a research on how to tune these parameters and how to get proper growth. So this reactive potential that was mainly prepared back in 2024 and by Dr. Van Duyn's group, and this was to capture the synthesis properties of these heterostructures. And the molybdenum part of it was actually already been evaluated by Dr. Van Duyn's group. This summer, I have done with the tungsten case, and I have seen that how this actually differs with the molybdenum, and this is proper differential with the experiments, and also like do I need to change the reactive potential or defeat the reactive potential? So the first thing that we did is we checked the carbon monoxide dissociation energies. So from tungsten hexacarbonyl, we take the carbon monoxide dissociation energies and also compared that with DFT data. And we can see that the initial 3 dissociation of carbon monoxide actually matched well with the DFT data, but the last 3 actually differed a little bit from the DFT data. But this is not actually that much bad because you can see the reactive always falls down the DFT results. That means the reactions is going to be should be a little bit faster, which is good for in our small scale simulations. And we compared the data with molybdenum structures, molybdenum species, and we can see that for the molybdenum species, the DFT and the reactive have actually matched well, at least for the first 5. The last one is actually the reactive shows higher energy, but the DFT shows the lower energy. With that, we went to some case studies. Like first case study, we had tungsten hexacarbonyl, and we heated up the tungsten hexacarbonyl in a box. So we had 100 molecules of tungsten hexacarbonyl in 100 by 100 by 100 angstrom cube box. And then we first minimized the structure. We did NVT relaxation at 300 Kelvin. We temperature ramped that structure to a required temperature and did NVT at that required temperature for another 2 nanoseconds. And from this energy versus time and temperature versus time graph, we can see that our parameters that we have chosen are actually not bad. They're very much good. And these are some results from that tungsten hexacarbonyl simulations. And we have compared them with the molybdenum ones. And we can see that the straight lines, those are the molybdenum ones, and the triangular ones are for the tungsten ones. And we can see that for the molybdenum ones, the carbon monoxide production was actually higher than the tungsten one. So we can say that the carbon monoxide production in tungsten precursors actually sluggish. And we can also see that some reactions are happening in lower temperature in molybdenum case, but in tungsten case, they're happening in higher temperatures, such as molybdenum tetracarbonyl to molybdenum tricarbonyl plus monoxide. That happens at around 1500 Kelvin, but around 1700 Kelvin, we see the same reaction as seen at 1750 Kelvin. I am sorry that there's actually a mistake because I forgot to put the temperatures in these curves, but the first one is for 1000, the second one is for 1250, the third one is for 1500, and the last one is for 1750. From there, we did our second case study where we had the same tungsten hexacarbonyl heat up, but this time with the presence of a monolayer. Now, this monolayer, we have added this monolayer as we added some sulfur vacancies in this monolayer. This monolayer is actually a tungsten disulfide monolayer and with some sulfur vacancies. Now, the reason we had sulfur vacancies because that would increase of the reaction time and increase the reaction and as well as the sulfur vacancies are the most stable vacancies in tungsten disulfide. And also the presence of the sulfur vacancies actually creates the opportunities for the tungsten anticides, which are good for nucleations to get multi-layer growth. Now we have added these monolayers in a box and added tungsten hexacarbonyl and the same box and heated up. And our expectation was that we will see the carbon monoxide being detached from tungsten hexacarbonyl, and that will eventually create tungsten anticides. But in this case, the similar case was seen in the molybdenum hexacarbonyl case. But in our case, we have seen that instead of the whole carbon monoxide decomposition, we just saw that only one oxygen is actually decomposed from the the tungsten carbon hexacarbonyl. And this oxygen actually oxidizes this tungsten disulfide surface, and and we can also see that later at some point later the tungsten hexacarbonyl one sulfur atom from the surface actually gets attached to the gas phase molecules. So we can see that our surface layer actually is being oxidized here, which is not seen in the molybdenum case. Now our next case study, we have added hydrogen sulfur in the presence of tungsten hexacarbonyl. So we had 400 molecules of hydrogen H2S, and we had tungsten hexacarbonyl. And from the graph at right bottom right, we can see that these are the curves, the species with presence of both tungsten and sulfur in it. So we can see that there are some species with tungsten and sulfur at the same time. That means there are some bonding sometimes. But one thing to notice is like this is actually not a bar chart. This is actually a line curve. That means after every picoseconds or every couple of picoseconds, you see that the species count actually going down to 0. That means that the species are not stable, the bondings are not stable. And I have found search for species and found the reaction part, and we can see that one tungsten pentacarbonyl get attached with one H2S, and after a couple of picoseconds, it gets differed again. So the molecules get separated again. But this case was not seen in molybdenum case. So in molybdenum sulfur case, so we have seen that there was actually stable bonds between molybdenum and sulfur. And eventually that also forms at last that forms like MOS2, MOS3, and also MOS4 species in it. The next case study, we have done some depositions of tungsten disulfide on tungsten disulfide layer. So what we have done is we had some, we can see that from here, from this curve, we added tungsten trisulfide on top of tungsten disulfide layers. And our expectation was that we will see a nice monolayer growth on top of the substrates, but instead we have seen some cluster-like structures and a lot of S2 gases flying over the vacuum. And we can see that there, after 7.5 nanoseconds, there was like 24 S2 gases, which was not seen in molybdenum case. And in our case, we can also see that there is some clusters instead of proper layer. So the question begins like, is the sulfur molecules actually from the gas phase molecules, the gas phase species, or is actually coming from the substrate layer itself? So for understanding that, we have done another kind of simulation. So we had, this time we had in a box, we had presence of tungsten trisulfide, and the density was almost 0.1 gram per cubic centimeter. And then we increased the temperature to 100 Kelvin, and we have seen that the amount of sulfur actually created by tungsten species actually double than the amount of sulfur molecule created by molybdenum species at 1000 Kelvin. And we can also see that the structures, the final structures that we get here is like for the tungsten sulfide, tungsten trisulfide case, we got some cluster-like structures. But in the case of molybdenum trisulfide case, we have seen some 2H good 2H nanosheet-like structure. And also this cluster, the stoichiometry is almost like 130 to 223, which is actually much less than 1:2 ratio. So we came to one conclusion that the sulfur and so the tungsten and sulfur maybe are more prone to 1:1 ratio in our according to our RSVP, which need to be corrected. And also we have heated up the one monolayer of sulfur dioxide to see that what happens when you heat it up. So when you heat it up around 1850 Kelvin, we see that there is like some sulfur molecules that are diffusing from the sulfur layer. Now this is not actually a perfect melting type of scenario. What we have observed in molybdenum disulfide case, where you see the ruptures and other things in the structures, which is actually more like a melting type structure, melting like behavior, but this is not a melting like behavior, but instead we see the sulfur molecules are actually getting decomposed from the monolayers. So with that, we have concluded our RSVP training for this summer, and the summary is like we have done the DFT calculations and matched with PXFF and have seen that the initial 3 carbon monoxide dissociation actually matches with the DFT results. And we have also seen that the production of carbon monoxide is slightly sluggish than molybdenum case. And we have seen that the sulfur dioxide is actually gets oxidized by tungsten disulfide monolayer is actually gets oxidized by tungsten hexacarbonyl. And we have also seen that there's no stable bonds between tungsten carbonyl and sulfur at this species. And we have seen that the tungsten trisulfide gas phase actually creates sulfur deprived structures. And I would like to thank my RSVP group, Dr. Colleague and Dr. Mayo, and also Dr. Van Duyn. And also I'd like to thank Martin for all his help. He's actually a graduate student of Pennsylvania State University. And I also like to thank my supervisor, Dr. Kasar Momini, for introducing me to this project. And as well as I would like to thank all of the people for this project and because of giving me the opportunity to collaborate and contribute to this group. Thank you, everyone.
Thank you, Rashidul. Are there any questions online or in the room?
I can ask one. For the reacts force fields, when the energies are different from the DFT, does that imply that the force fields need to be trained more, or is there a particular reason that they would differ?
So the force field, actually our conclusion was that the force field need to be trained more because our that prediction that we actually made actually was wrong. Like we didn't see any kind of like molecular structures getting from the deposition. So our prediction was like we need to change this force field, need to retain this force field. But in this case, like the DFT results and the reactive result, actually this is not that much bad. So we can say that it's not that much bad. So we don't need to retain it for in this case. But if we need more accuracy, then it's obviously better to retrain it.
Okay. Thank you.
Thank you again, Rashidul. Our next talk will be from Maryam Esfidani from the University of Iowa. And Maryam, you are good to begin as soon as you're ready. Thanks.
Great, thank you. Share my screen. Hello everyone, I'm Maryam Vaghefi, a grad student at the University of Iowa working with Professor Fairlamb. I have this great opportunity to work with Professor Law and Professor Redman during the summer for growing thin film and developing liftoff process. So I'm going to explain a little bit about the work we're doing here, why we come up with this idea, and then what we've done in Penn State. So my PhD project is about developing photonic devices, and it's all about the light matter interaction and localized electromagnetic field. So we choose the right material, design, simulate, and fabricate metamaterial and waveguide, and then we characterize them using the optical spectroscopy. So here you can see the quantum well infrared photodiode detector. That's a sandwich of aluminum, gallium arsenide, and gallium arsenide. The other work we've done is tuning the waveguide to improve the efficiency and also tune the wave number and modes. So we play with the geometry of the waveguide. And also we invent a hydrogen sensor. So we use a metamaterial to detect the hydrogen. The other work I'm doing here as my PhD project is developing the spectroscopy tools. So we can look at this photonic device and also 2D material at a low and high temperature. We can go down to 4K and also see the energy momentum of the emitter. So we can see the emission pattern because these are the waveguide and photonic devices. So the observation angle is really important. So what brings us to this program is developing these detectors. So we already have the grating on top of the detector, and based on the simulation, we know that detector going to improve by a factor of 19. And then we come up with this idea, if we have a very thin film on top of that, how that detector going to improve. And even we have a grating on top of this thin film. So as a proof of concept, you start with tin selenide and gallium arsenide. So growing them, characterize them to make sure they have a good quality. And then at the end, we propose to lift off this tin selenide and transfer it to the desired substrate. So in why we choose gallium arsenide and tin selenide. So these are the polar semiconductor and anisotropic. So they are very sensitive to the polarization and they have a tunable band gap. So in order to making these devices, like a photonic devices, these are the very good choices. So we start with molecular beam epitaxy to grow tin selenide and gallium selenide. So the way it works, there are different cells here, and this is a very high vacuum system. And sample going to be a mount here. Let me, oh, my laser point. So sample gonna mount here. It can be heat up. It will be heat up during the process, and it's gonna be rotate. So we're gonna end up with a very uniform, high quality film. There is a read gun and a read detector. So it's like a real monitoring of the process. If something goes wrong, we can just shut down the process, correct the recipe, and then start again. So the way it works is going to shoot the electron to the sample, and then detector going to capture all the electrons. So there are different calibration we can do, like different parameters. We can play with the temperature of the sample. We can play with the flux ratio and grow rate. So for the tin selenide, we start with developing the recipe with 1 steps and 2 steps. So since this is the recipe development, we have lots of results. I just picked some of them. So this is the one, we change the temperature of the sample. And you can see by changing the temperature of the sample, the film quality getting better, and also read pattern confirm that. Then we play with the flux ratio. I don't think I need to explain about this. You can see how film quality improved by changing the flux ratio. Also, this is like, as I said, this is the recipe development. So this is not just we play with the flux ratio. I think at this result, we also change with the substrate temperature. And then at the end, we could get the tin selenide with the thickness of 14 nanometers. And here you can see the XRR data that confirm the thickness, and also XRD, very sharp, nice tin selenide peaks, and also read patterns confirm that. The other things we try is growing the tin selenide with 2 steps to just improve the film quality. And here we play with the annealing time and also the temperature. And you can see the film quality, it gets a lot better. And then we did the same things for growing the gallium selenide. And then this is a result we have. So that recipe is kind of already developed in Professor Law's group. And here we could grow the different thickness of gallium selenide. The next step was lift off and transfer this thin film. So the reason we're doing this because this is about improving the photonic devices, right? So most of the time, the donor substrate is not good for making the devices because they don't show the interesting optical thing for making these devices. So we need to transfer them to the desired substrate. So the problem with transferring this thin film, if you look at this data right here, these have a very low exfoliation energy, and these are the material people play with it so far. However, even with this material, they can transfer it in order of the few microns, and this has an unpredictable domain size, and surface usually damage, even with this low exfoliation energy. So here we are interested to look at the tin selenide, this one right there, and then exfoliation energy is about 32, so a lot higher compared to this one. And then that was part of my program I've done in Penn State. And here is the result we have. So we could transfer the, so the substrate we grow was like around 1 centimeter by 1 centimeter, and we could lift off the entire thin film without any tear, without any damage. And then we could transfer it to the different substrate like a gold and silicon. This is just a sample. We can transfer to any substrate we would like to. And also Romita confirmed our data. So at that time, because I have the limitation to go through the fab facilities, you can also see some peaks from the PMMA here because I need to clean up with the acetone and ethanol. But however, we can see the Raman spectra for the tin selenide. So it's confirmed that we have the tin selenide here, and also AFM data show the field. And at the end, I want to thank you for everyone who helped me for this process. And I'm happy to take any question if you have.
Thank you, Maryam. Does anyone online or in the room have a question?
may have a question.
Go ahead.
Have you done any rocking curve, XRD rocking curve to just see the FWHM of your 10 solenoid film or any fire scan on that or no? Just curious to know.
Sorry, he's kind of breaking up. Could you please repeat his question?
Have you done any rocking curve measurement to just see how much is the FWHM of the tin solenoid film, or just fire scan on the film and B films?
Of the transfer sample?
Yes.
No, we measure it with AFM. And then, so the thickness, the one we transfer, the original one was 14 nanometers. And the thickness of the transfer was varied because, so this is the plan we have to make a measurement on the actual sample because those are the XRR data we have. So we have the general overview of the sample, if you know what I mean. But for this sample, we go with the AFM because we don't have the XRR here, and we measure it. So that was like 12 nanometers. So we kind of want to know if this is the actual 12 or maybe a little bit vary around the sample, like actual sample. So some part may be 14 nanometers, some part might be 12 nanometers. You know, thickness might be vary around the sample. But in the AFM data, that was 12 nanometers. So we might missing 2 nanometers, or maybe at that point, that was 12 nanometers. We don't know that. But overall, what we can say is like we're transferring the entire film. We're not missing anything here.
Gotcha. Thank you so much.
And there's another question online, Maryam, in the chat. They would like to know if you could please give an idea of the problems generally faced during transfer.
Let me just give the idea of the problem we generally face. Generally, how generally are you asking? I don't know
Well,
what
what
that
did
means.
you-
Could you explain more?
Well, what were your biggest problems or hurdles you had to overcome?
So the biggest problem here, at least for this process, is transferring to the desired substrate. If you look at this data right here, it'll show you this image. You see that film is completely lift off, right? So we have a very nice thin film lift off here. But transferring to the desired substrate, you know, we're missing some part of this. With developing this, I don't have our new data here. It's getting a lot better. But seeing this nice uniform film here and then transferring like this is kind of disappointing. So if I wanna ask this question, I'm gonna say transferring part is kind of hard.
So getting complete film transfer is the biggest issue that you see right now?
Yeah, I think so, yeah.
Okay, thank you.
Sure.
Awesome. So then our next speaker will be Dr. Sahil Gasso from Florida International University. And Sahil, you're good to go ahead and share your screen and get started as soon as you're ready.
Thank you so much, Kelsey. Okay. There you go. Are you able to see my screen?
Yep, it's perfect.
Okay. Hi. Hello, everyone. Good afternoon. My name is Sahil Gasso. I am a postdoctoral associate working with Dr. Kenyon at Florida International University. So through this 2D CC program, I got the opportunity to learn the bulk crystal growth. And perfectly for this particular bulk crystal growth, we focused on RB doped sylvanite, and the sylvanite material which I showed is copper niobium sulfate using the advanced techniques. Going through the highlights of my presentation, so I'm trying to fabricate a single crystal using bulk crystal growth because these bulk crystal growths are good technique because they have they don't have any defects. for advanced optoelectronic applications. And this is the one of the most effective method to control stoichiometry, morphology, and defect density of the crystals. So with this, I got the opportunity to work with Professor Mao at Penn State Research Group. So Professor Mao has a specialty in growing these bulk crystals using different techniques like melt, CVT, flux, Bridgman, and floating zone methods. So I have learned few of these methods like melt, CVT, flux, which I will discuss in my further slides. So in today's presentation, I'll focus on the sealing station. Yes. Okay, where are you? Pointer. Okay, I'm just getting my point. Never mind. Okay, so in today's presentation, I'll focus on the sealing quad station, then three different bulk growth methods, the melt crystal, flux crystal growth, and chemical vapor transport. So moving first to the first crystal growth, which is, I'm not able to, okay. So first one, I'll discuss the sealing station. So there are different components in the sealing station. The very first one over here is the torch, which is connected to a hydrogen and oxygen cylinder. And we use this torch to seal our quartz tube. The second one are the quartz tube holders, which are used to hold the quartz tube containing the material to seal it. The third one is the Pirani and the panning gauge, which are used for the rotary pump and the turbomolecular pump. Fourth one, we have the valve to control the vacuum going to the quartz tube holder and towards the vacuum pump. Then we have a vacuum trap, which contains the liquid nitrogen that is used to trap any contaminant going back to the vacuum pump so that we don't need to disturb our vacuum pumps. And the sixth one is we have the vacuum pump. So mainly I have used rotary pump and the turbomolecular pump at Penn State. Based on this, we have made our own sealing station at FIU, where we have only the rotary pump and two of these quartz tube holders. So here you can see the sealed quartz tubes of RES2 and MOS2. And for this particular project, apart from rubidium doped copper niobium sulfate, I have synthesized some other materials like ruhenium disulfide, molybdenum disulfide, rubidium copper niobium tetrasulfide, copper niobium tetrasulfide, and triniobium dicopper hexasulfide. Moving forward to our first crystal growth, which I have learned is the melt crystal growth. So it's more like a solid state reaction where we want to homogeneously mix the individual elements inside a vacuum sealed quartz tube for further growth treatments like CVT and flux. So usually we made a 4 to 5 inch big quartz tube and put it in the muffle furnace, maintaining an operating temperature higher than the melting point of the elements. So for example, for this, I have used different concentration of ruhenium and sulfur for ruhenium disulfide, molybdenum and sulfur for molybdenum disulfide, indium and selenide for indium selenide, and copper niobium sulfur for copper niobium sulfate and niobium copper hexasulfide. So I have presented one a temperature profile for RES2. So we heated up the RES2 from room temperature to 1000 degrees C and maintained there for 7 days so that RE and sulfur homogeneously mix inside that quartz tube. And after that, we just slowly cool it down to room temperature and go with the other growth treatments. Moving forward to the second growth, which I have learned at Penn State, is the bulk crystal growth. For bulk crystal growth, we are the second one is the flux growth. Yeah. So for flux, we need a low melting point metal solvent. So I have used antimony, which is used as a flux to growing these crystals. So for this particular method, we need alumina crucibles, and we pour all our elements in that and then load this alumina crucible inside the quartz tube, as you can see over here. And on top of that, we put some quartz glue. So similarly, the size of these quartz tubes are around 4 to 5 inches long, so that we can easily put it inside the muffle furnace. But the difference here is that we increase the temperature of this furnace higher than the melting point of the material, and the melting point or the operating temperature needs to be higher than the melting point of flux. So but in this case, the melting point of antimony is 650 degrees C. So you can see from the temperature profile, we ramp up the quartz to 950, which is higher than 650, the melting point of antimony, and slowly cool it down to 750. So 750 is still higher than the melting point of antimony. And at this particular temperature, we need to centrifuge our material, our quartz tubes, because we need to remove the residual flux, which is antimony, out of our target material. So here we use flux as a main material to grow the crystals, to grow the bulk crystals. The third technique, which is a CVT technique, which I have learned at Penn State. In this, we need to have some transport agents, like halogen transport agent, like iodine and bromine, that react with the target material to form volatile gaseous compounds that migrate along the temperature gradient in a sealed quartz tube to facilitate single crystal growth. As you can see over here, so we have a source material, and along with that we inserted iodine or bromine as a transport agent, and you can see we have a hot and the cold zone, and we are getting the crystal at the very end of the hot zone. So the target material and the transport agent were placed in a 7-inch long quartz ampule, which are subsequently sealed under vacuum. For this, we need a long tube, because we are using tubular furnace in comparison to the other furnace which we have used, like the muffle furnace for the flux growth and the melt growth. So for tubular furnace, we need a long tube to grow the crystals. And again, the sealed ampules were heated in a 2-zone or 4-zone tubular furnace, maintaining a temperature gradient between the hot zone and the cold zone. As you can see for the temperature profile of RES2, the cold and the hot zone at 1010, like 1010 and 1060. So far I have discussed the sealing station and the different methods I have learned to grow the bulk crystals. So moving forward, I'll showing you the results. So first I'll go with the RES2. So you can see from the XRD and the EDS, the XRD pattern confirms the formation of RES2 with this JCPDS card number. And from the EDS, the RE and S is uniformly or homogeneously distributed all over the surface. Along with that, the atomic ratio of RE and S is in 1:2, which is desired. Then for the flux growth, antimony flux was used to grow rubidium doped copper niobium sulfate crystals with 0.3 and 30 mole% antimony via flux method. Interestingly, without antimony, like 0% antimony and 0%, I just label it as 0% antimony and 0% antimony _1. So we are able to grow 2 different types of crystal in the same batch. So the 0% antimony has rubidium in it. On the other hand, the 0% antimony _1 doesn't have rubidium in it, which is kind of interesting. So moving forward with the higher doping concentration, which is 3% and 30% antimony assisted rubidium copper niobium sulfate, you can see the all the materials are uniformly distributed, and there is the atomic weights are for sulfur, niobium, and rubidium copper changes with the different antimony concentration. So based on this, I did the XRD, and interestingly, as I mentioned, there are different types of growth for there is a different type of XRD pattern for 0% SB and 0% SB1 inside the same quartz tube. and the crystals obtained from 3 molar are very small, resulting in a weak XRD reflections. And the crystal structure for 0% SB performs the monoclinic crystal structure, whereas the 0% SB goes with the hexagonal. On the other hand, the 30% SB gives the mixed phases of copper, niobium sulfate, and niobium sulfate. And the EDS analysis confirmed the presence of rubidium, copper, niobium, and sulfur in all the samples. While optimizing the growth of these materials, we came up with a very exciting hexagonal shaped crystals without RB, which is copper niobium sulfate. As you can see in the picture, we have a very big and beautiful hexagonal shaped crystal structure, and through the SEM images, you can see the hexagonal shaped geometry. So we are trying to synthesize. We have tried to synthesize these two crystals, and the XRD pattern confirm the formation of hexagonal crystal structure. And through the EDS, the sulfur, niobium, and copper uniformly distributed all over the surface. And the atomic percentage of this Cu2NbS4 gives approximately 0.65 ratio to 1:2 for copper niobium sulfate. So we can say that it's copper doped niobium sulfate. Moving forward with niobium copper sulfate, we have get the same results where the copper niobium sulfur are uniformly distributed all over the surface, and I have tested at 2 different crystals, but I'm getting almost the same results. So based on this, I'm summarizing my results that we successfully synthesized single crystal of RES2 copper doped niobium sulfate using melt, flux, and CVT methods. And we are still working on synthesizing this rubidium doped solvenites. The XRD confirmed the structural and the phase formation. EDS validates the elemental composition. In the future work, we grow and optimize additional bulk crystals, bulk single crystals, and employ state-of-the-art techniques like XPS, Raman, TEM, AFM to probe structural, electronic, and surface property, and explore these crystals for the application in optoelectronics and quantum technologies. I would like to specially thank Dr. Sangyu Lee Sam, Dr. Ron Kingdon, and other group members for their consistent support in teaching the bulk crystal growth techniques. And I would like to thank Kelsey and Professor Redwing and all the members of 2DCC for their continuous support. Thank you.
Thank you, Sahil. Are there any questions? Okay, so our final talk will be from Dr. Navdeep Kaur, who is also from Florida International University. And Navdeep, you are good to share your screen and begin as soon as you're ready.
Hello, everyone. Good afternoon. My name is Navdeep Kaur, and I'm a postdoc at Florida International University. I work with Dr. Daniela Radu, and during this summer, I got an opportunity through 2DCC RSVP program to visit Penn State University and visit Dr. Jones' lab and learn how to do the exfoliation of bulk crystals. And I learned Scotch tape exfoliation procedure and learned how to use the transfer stage to pick the monolayers or multi-layers of exfoliated materials, and did learn how to do the EFM imaging to estimate the thickness of the layers that we exfoliate. And also we did try to fabricate the devices out of it to understand the electrical properties of the materials. And during my visit there, I learned the Scotch tape technique, which is basically the traditional method of doing the exfoliation from the bulk crystals to obtain the monolayers of the materials. And this is the this is the RES2 crystal which we bought, and then we used this this material and using the Scotch tape, and we put this crystal onto the Scotch tape, and with the repeated folding and unfolding of the Scotch tape, we did get basically layers of it's all over the Scotch tape. And we do this is the exfoliation procedure which we used, and then we wanted to transfer those exfoliated layers onto the substrates. In our case, we use the silicon substrates, but we did pre-clean those substrates before. And for the pre-cleaning, like we did use the ozone cleaning, and we sonicated the material, the silicon substrates in acetone and IPA for proper cleaning procedure, which is a standard one. And then we put the scotch tape having the exfoliated material onto it, which is the RES2, onto the silicon substrates, and then slowly peeled off at 180-degree angle and to transfer the layers onto the silicon substrates. So after the transferring of the exfoliated layers onto the silicon substrate, we did the using the transfer stage setup, which is the HQ graphene transfer stage. We did use the optical microscope to first see what kind of layers did we get from those material onto the silicon substrates, and wanted to look into the kind of monolayers which we could use for further device testing. So here is the different magnification images or optical images of the material. Like we could find a 10x4 microns layer, which we were not expecting it to be a monolayer, but it could be a multi-layers. So in order to how we did this, we wanted to actually transfer this layer, 10x4 micron layer, multi-layers onto different substrates. So in order to do that, we had to prepare the stamps, which is basically made using two different polymers. First, we needed to make a PDMS domes, which is polydimethyl silicooxane. And this domes, how do we prepare it? We take a mixture of 12:1 silicon elastomer, and we did mix them thoroughly and then keep it overnight to cure. And then next day morning, we did use a cylindrical cutter to just make a small cylindrical cuts into it. And then using the same PDMS solution, we did drop like 2-3 drops onto these cut circular shaped PDMS domes, and then and then we keep it overnight to cure, and that's how we prepare the PDMS domes. And the second one is the PC layer, which is the polybisphenol A carbonate layer. We prepare it by using a PC solution in chloroform, and we did use a few drops, like 4 to 5 drops onto a one glass slide, and take another glass slide, and then put them on together onto each other, and then slightly sliding it from one end to the other, so that we have two layers, a layer of PC material onto both the glass slides, and then we leave them onto a flat surface overnight to make sure that to cure the PC layer. And then how to make the stamp. For the stamp formation, we actually we took a punched Kapton tape onto a glass slide, and took the one small piece of PDMS dome on and put it onto the punched area. And we wanted to align the punched area with the PDMS dome. And then we took, using a scotch tape, we took a layer of PC material from the glass slide and put it onto the punched PDMS dome, and this is how the stamp was prepared. And this stamp was basically used to pick the layers of the exfoliated material from the silicon substrate using a HQ graphene transfer stage, which was in glove box. And I learned how to use this transfer stage. Along with this, I learned how to build an in-house transfer stage setup using different components, and which we are probably trying to set up at FIU in our lab. And after we exfoliate the material and put it onto the silicon substrate, we wanted to basically know what kind of thickness do we get for those layers. So in order to do that, we learned how to do, we did the AFM images, and this is the AFM images of one of the layers. We tried to find a kind of area where we do have a staircase kind of thing, so that when we do the height profilometry, and the step size would provide us an idea of how thick the layer could be. In our case here, it was nearly 8 nanometer, and we are expecting that the number of layers here, it would be nearly 8 to 10 layers. So we wanted to transfer that 10 by 4 micron layers, which were like multi-layers now. We wanted to transfer it from the silicon substrate to platinum electrodes, which we have used. This is the image for those platinum electrodes which we used, and we using the same transfer state setter, we basically transferred pick the from the PDMS dome, which we used like to pick the flake from the silicon substrates, and then we put it onto this platinum electrodes, and then we did do the electrical measurements of the material, and it seemed to be showing an ohmic behavior with the resistance, which is pretty much higher, nearly 4 into 10 plus 6 ohms. And we did at PhD at Penn State, I got an opportunity. I'm thankful to Dr. John Renwing and Dr. Yiru Yu, who showed me their lab and showed me the cryogenic system that they have used for Raman and PL instrument, and which is the technique which we are going to use to basically check how many layers did we exfoliate it from the exfoliation technique, and how much did we after the exfoliation after transferring it from the one substrate to the another substrate. And then I'm thankful to basically Dr. Nathan's lab, and Sandra was kind enough to show me her lab and show me the molecular beam epitaxy sample transfer stages and STMs, and also the IPS instrument, and they showed me how they are using this technique to understand the electronic properties and of the material that we prepared there. And finally, I'm thankful to all the 2DCC RSVP program members and Dr. June, Patrick, John Renwick, and Dr. Drew, Anthony, Nathan, and everyone who basically helped me throughout my visit at Penn State. Thank you.
Thank you, Navdeep. Are there any questions? Okay, so in closing, I just want to thank all of the RSVP presenters today for your time and efforts. And then I also want to thank all of the RSVP hosts who always go above and beyond for this program. We're very appreciative of all your help. And we want to remind everyone that the application deadline for visits next year is January 31st of 2026. And we encourage you to work with any potential future host on your application. And if you have any questions, you can always ask Dr. Ron Redwing or myself. And thanks again, everyone. Bye.
Thank you.